Good morning, everyone. Over the past few lectures, we have built a comprehensive understanding of external flows. We started with the general characteristics, how Reynolds number determines whether the flow is inertia dominated or viscosity dominated. Then we dove deep into boundary layers concept, that thin region adjacent to the surfaces where the viscous effects concentrate. Last time we explored the drag concept, the force in the direction of the flow that resists the motion through a fluid. So today we turn our attention to other component of the force vector, that is the lift. While drag is something we usually want to minimize, lift is something we often want to maximize. It's what keeps the airplanes in the air, allows the bird to soar, and even explains why some pitches in the baseball curve unexpectedly. But here is the fascinating part. Lift is not just for wings. It appears in unexpected places, on buildings, on race cars, on spinning golf balls. Understanding lift means understanding how pressure distributions around objects can create forces perpendicular to the flow direction. So where does the lift comes from? Let us go back to the fundamentals from this particular equation. The lift on any object is the integral of the pressure sine of theta times dA plus integral of the shear stress, wall shear stress cos of theta times dA. So lift comes from two sources: pressure forces acting normal to the surface and the pressure forces acting tangentially. The sine and cosine terms tells us that the contribution of each depends on the surface orientation. For most objects operating at high Reynolds numbers, airplanes, race cars, even bird wings, the flow has a boundary layer character. Viscous effects are confined to thin boundary layers and wake regions. In these cases, the wall shear stress contributes to very little to lift. The vast majority of lift comes from the surface pressure distribution. So this is the crucial point. Lift is primarily a pressure phenomena. The shear stress, while essential for understanding the boundary layer behavior and drag, plays a minimal role in generating lift at high Reynolds number. So at very low Reynolds number value, think microscopic organisms swimming or tiny insects flying. Here, viscous effects dominate everywhere, and shear stress can be as important as pressure in generating lifts. But for our purposes, we will focus on the high Reynolds number regime where most practical lift generating devices operate. Now, to understand how pressure creates lift, look at this particular figure, the pressure distribution on an automobile. This is not a wing, but it perfectly illustrates the principle. The figure uses color coding. Red areas denote uh, pressure higher than the atmospheric, blue areas denote the pressure lower than the atmospheric. At the front grille and the base of the windshield, air stagnates, it slows down, and the pressure increases. These are high pressure regions. Over the hood, the roof, and particularly over the rear window, air accelerates. According to Bernoulli's equation, where velocity increases, pressure decreases, these are low pressure regions. Now look at the overall pattern. The low pressure areas on the top surfaces are larger and more extensive than the high pressure areas on the bottom. When you integrate this pressure distribution over the entire car surface, you get a net upward force, which is the lift. For a typical passenger car, this lift is undesirable. It reduces tire traction and affects handling. That's why some cars and add spoilers or aerodynamic devices to manage the pressure distribution and reduce lift, or even create negative lift downforce that pushes the car onto the road. Now, for an airplane wing, the pressure distribution is deliberately designed to maximize this effect. The upper surface is curved more than the lower surface, causing the air to accelerate more over the top, creating lower pressure there. The result is a net upward force, exactly what we want for flight. Now, defining the lift coefficient, just as with the drag, we express lift in dimensionless form using the lift coefficient as CL equals to lift force divided by half rho u square times the area, where area is here the characteristic area. For airfoils and wings, this is typically the planform area, the projected area seen from the above, where which is the wingspan times the average chord length. So why the planform area rather than the frontal area? Because for a thin wing, the frontal area is very small, just the leading edge thickness times the span. Using planform area gives more meaningful coefficient values, typically on the order of unity. A lift coefficient of 1 means the lift force equals the dynamic pressure times the wing area. So the lift coefficient depends on the same dimensionless parameters as the drag coefficient, which is a shape, Reynolds number, Mach number, Froude number, and roughness over length, E over L. Sorry, epsilon over L. But in practice, shape is by far the most important one. Reynolds number effects are often minor for lift at very high Reynolds number values, but Mach number matters only at high subsonic and supersonic speeds. Froude number matters only for surfaces near a free surface like hydrofoils and surface roughness typically affects the drag much more than the lift. So the primary way we control lift is by changing the shape either through the design of the airfoil itself or by changing its orientation relative to the flow. Now the airfoil geometry and angle of attack, as shown in this particular figure, it shows actually two fundamental airfoil shapes. The first is symmetrical. The upper and lower surfaces are mirror images. At zero angle of attack, meaning the chord line is parallel to the oncoming flow, the pressure distributions on the top and bottom are identical. They produce equal and opposite forces in the vertical direction, so the net lift is zero. A symmetrical airfoil produces lift only when it's inclined to the flow, when it has a positive angle of attack denoted by alpha. But the second is cambered or non-symmetrical shape. The upper surface here has more curvature than the lower surface. Even at zero angle of attack, the symmetry in shape creates asymmetry in the pressure distribution. Air accelerates more over the curved top surface, creating lower pressure there. This results is the result is that the positive lift even when the chord line is parallel to the flow. So for such an airfoil, there will be some negative angle of attack, some nose down orientation where the lift becomes zero. At that angle, the integrated pressure forces on upper and lower surfaces, though different in distribution, produce equal and opposite vertical components. So the key concept over here is that the lift is generated by creating a pressure imbalance between the upper and lower surfaces, whether that imbalance comes from camber, from angle of attack, or from both. The result is the same, a net force perpendicular to the flow. Now, lift coefficient versus angle of attack, we would be looking at this particular figure part A, which shows the lift coefficient as a function of angle of attack for airfoils of different aspect ratios. The behavior is remarkably linear over a wide range. As the angle of attack increases, the lift coefficient increases proportionally. The slope of this line is the fundamental characteristic of the airfoil. But notice what happens at a higher angle of attack. Eventually, the curve stops increasing, reaches a maximum and then drops sharply. This is stall point, one of the most critical phenomenon aerodynamics. What's happening physically over here, we would be returning to the earlier figure from earlier topic in this particular section. At moderate angles of attack, the flow remains attached over most of the upper surface. The boundary layer survives the adverse pressure gradient over the rear portion and makes it to the trailing edge. But at the high angle of attacks, as shown in the part B of this figure, the adverse pressure gradient becomes too severe. The boundary layer separates from the upper surface, creating a massive wake of recirculating flow. Lift drops dramatically and drag increases sharply. So this is why stall is dangerous, especially during takeoff and landing when aircraft are close to the ground. This loss of lift can be catastrophic if there is no altitude to recover. So this particular figure shows the same data in different forms: lift to drag ratio versus the angle of attack and the lift drag polar. The maximum lift to drag ratio represents the most efficient flight condition. For high performance airfoils, L by D can exceed the value of 100, meaning that the airfoil generates 100 units of lift for every 1 unit of drag. Now, the role of the wingspan is very important, as this particular figure is showing the effect of the aspect ratio denoted by the capital A with a bar over it, defined as the span squared divided by the planform area. So for a rectangular wing, this simplifies to span divided by the chord length. Higher aspect ratio means longer, narrower wings. The albatross, with its enormous wingspans relative to the chord, has a very high aspect ratio. A fighter jet with short, stubby wings for maneuverability has a low aspect ratio. The data shows that higher aspect ratio gives higher lift coefficient at the same angle of attack and lower drag coefficient. But why? Because of induced drag, drag associated with the generation of the lift. At the tips of any finite wing, there is a pressure difference between the lower surface, higher pressure over there, and upper surface where there is lower pressure. So this pressure difference causes the air to leak around the tip, creating swirling vortices that trail downstream. These trailing vortices contain kinetic energy that must be supplied by the aircraft's engines manifested as additional drag. Now, longer wings have smaller tip effects relative to their total area, so induced drag is lower. This is why gliders and long-range aircrafts have very high aspect ratios. They prioritize efficiency over maneuverability. Now, modern aircraft don't rely on a fixed shape. This particular figure, as it is showing the leading edge and trailing edge flaps, the devices that temporarily change the airfoil shape to increase the lift when needed. During takeoff and landing, aircraft fly at relatively lower speeds. To generate enough lift at these speeds, they need higher lift coefficients. Deploying flaps increases the camber and effective area of the wing, dramatically increasing the maximum lift coefficient. So this comes at a cost. Flaps also increases the drag significantly. That's why they are retracted during the cruise uh, position when the aircraft flies fast enough that the basic wing shape provides sufficient lift with low drag. The high drag dirty configuration is only used when needed during the low speed phases of the flight. So this concept of shape changes for performance optimization appears throughout engineering, from variable geometry aircraft to morphing wing concepts being researched today. Now, moving on to the circulation concept, we need to address the fundamental question. How do we explain lift theoretically? If we try to calculate the inviscid flow past an airfoil using potential flow theory, we run into a problem. As this figure illustrates this, for a symmetrical airfoil at zero angle of attack, in the part A of this particular figure, the potential flow gives a reasonable result. The streamlines are smooth and the flow behaves as expected. But for the same airfoil at the non-zero angle of attack, The part B of this particular figure, potential flow predicts something unrealistic. The flow goes around the trailing edge from the lower surface to the upper surface with an extremely high velocity and a stagnation point somewhere on the upper surface. So this does not match what we observe experimentally. More importantly, the potential flow predicts zero lift for this configuration, which we know is wrong. But for real airfoils at positive angle of attack definitely produces the lift. The solution developed by early aerodynamicists is to add the circulation, a swirling flow around the airfoil. As part D of this particular figure is showing this concept, uniform flow plus circulation equals the realistic flow pattern as depicted in part C of this figure. Now, adding clockwise circulation increases velocity on the upper surface where the circulation adds to the flow and decreases the velocity on the lower surface where it opposes the flow. So, from Bernoulli equation, higher velocity means lower pressure at the top, lower velocity means higher pressure on the bottom, exactly the pressure distribution that produces the lift. The amount of the circulation needed is not arbitrary. It's determined by the Kotak condition with which requires that the flow leaves the trailing edge smoothly with equal velocities on the upper and the lower surfaces at that point. This condition uniquely determines the circulation for a given airfoil shape and angle of attack. While adding circulation might seem like mathematical trick, it has solid physical foundations, as we will see in the next slide, which is the physical reality of the circulation in terms of the wingtip vortices. Now, this particular figure is showing what actually happens on the finite wing. Because of the pressure difference between lower and upper surfaces, air leaks around the wing tips, creating trailing vortices. These vortices are connected by the bound vortex along the wingspan, together forming a horseshoe vortex system. The strength of this vortex system, this circulation is directly proportional to the lift generated. Large aircraft like the Boeing 747 produce tremendously strong trailing vortices that persist for miles behind them. These vortices are powerful enough to flip smaller aircraft that fly too close behind, which is why air traffic control enforces separation distances based on the aircraft weight categories. So the photo in this particular slide shows a trailing vortex visualized by the smoke, a beautiful demonstration of the physical reality of circulation. So this vortex system also explains induced drag. The trailing vortices represent kinetic energy that must be supplied by the aircraft's engine. The downwash they create tilts the effective lift vector slightly backward, creating a drag component. This is the price we pay for generating lift. Interestingly, some birds fly in V formation, especially to take advantage of these vortices. Each bird positions itself to catch the updraft from the vortex of the bird behind it, reducing its own energy expenditure. Studies suggest that a flock of 25 birds flying in formation could travel 70% farther than the same birds flying separately. That is the nature's version of drag reduction. So, circulation is not limited to airfoils, it can be generated on symmetrical objects if they rotate. This is the Magnus effect, named after Heinrich Magnus, who first investigated it in the 19th century. Now, this particular figure shows the concept. Part A of this figure shows the inviscid flow past a stationary cylinder, perfectly symmetrical, zero lift and zero drag. But part B shows a free vortex at the center of the cylinder, pure circulation without any through flow. And the part C combines the uniform flow with circulation. The resulting flow is no longer symmetrical. On the top, of it, the circulation adds the flow velocity. On the bottom, it subtracts. Higher velocity on the top means lower pressure, but lower velocity on the bottom means higher pressure. The result is that a net upward lift force generates. In a real viscous fluid, rotating a cylinder drags fluid around with it due to viscosity, creating circulation effect. So the same principle applies to spheres, which is why spinning balls curve in flight. This particular figure shows lift and drag coefficients for a spinning smooth sphere as a function of the spin parameter, which is omega d by 2 capital U. The lift coefficient increases with spin rate, more rotation, more circulation, more resulting lift coefficient. So the drag coefficient, interestingly, is relatively insensitive to spin. Now, real world examples, applications like curveballs, golf, and more. So this explains countless phenomena in sports. Baseball, a pitcher throwing a curveball imparts a top spin, backspin, or side spin. So the Magnus effect creates a force perpendicular to both the spin axis and the flight direction, causing the ball to curve. A fast ball, on the other hand, with backspin, actually experiences upward lift, making it appear to rise through its really just falling slower than the gravity would predict. A knuckleball thrown with minimal spin does not benefit from Magnus effect. Instead, it seems to interact with the boundary layer in complex ways, creating unpredictable movement. The another example is of the soccer, where players learn to blend the ball around defensive walls by striking it off center, imparting spin that curves the trajectory. When we see the golf example where a driver imparts backspin, creating lift that helps the ball stay airborne longer, combined with the dimple induced drag reduction we discussed last time. This is why golf balls travel so far. A well-struck drive might have a trajectory that actually rises initially before gravity and drag bring it down. Another example is of the tennis, where topspin causes the ball to dip faster than gravity alone, allowing the players to hit with more power while keeping the ball in court. Slice shots curve sideways. In all of these cases, the boundary layer plays a crucial role. The roughness of the ball seams on a baseball, dimples on a golf ball, fuzz on a tennis ball affects how the boundary layer behaves and how much circulation is generated for a given spin rate. So now let us summarize what we have learned about lift is that lift is primarily a pressure phenomena, the integrated effect of pressure distributions on upper and lower surfaces. The lift coefficient relates lift to dynamic pressure and platform area by the relationship as CL equals to lift force divided by half rho u square times A. Lift depends strongly on the shape, camber, and angle of attack are primary variables. At high angle of attack, this boundary layer separation causes stall, a catastrophic loss of lift. Then we discussed that higher aspect ratio wings are more efficient with less induced drag. Circulation theory explains lift mathematically, adding appropriate circulation to potential flow gives realistic pressure distributions. Then we discussed that trailing vortices are the physical manifestation of circulation effect, connecting lift generation to induced drag. Then at the end, we discussed about the Magnus effect showing that the rotating symmetrical objects can also generate lift through circulation. Next time, we will conclude our study of external flows by bringing all these concepts together. We will look at some comprehensive examples explore additional applications, and see how these principles of boundary layer drag and lift apply to real world engineering problems from aircraft design to wind engineering to sport equipment. So for today, remember that the lift is not a magic. It's the logical result of the pressure distributions shaped by the geometry and flow conditions. Whether it's a 747 carrying hundreds of passengers across oceans, a baseball curving past a better, or a race car spoiler pushing the vehicle onto the track, the same fundamental principles apply there. The boundary layer, which we studied in such detail, plays a crucial and critical role, not by contributing directly to lift, but by determining when and where the flow separates. Without understanding the boundary layers, we cannot understand the stall phenomena. Without understanding the stall phenomena, we cannot even design safe, efficient lifting surfaces. So this is all for now. In the next, we would be moving on to external flow characteristics. Thank you very much.